Here we're going to show that complex exponentials defined through Euler's formula satisfy all the usual rules of exponentials. Euler says that e to the j theta equals cosine theta plus j times sine of theta. Now I'll list four properties that complex exponentials should satisfy. 1. E to the j times 0 equals 1. This is obvious. E to the 0 should be 1. Let's prove that right here. It only takes one line. E to the j is 0. If we plug that into Euler's formula, we get cosine of 0 plus j times sine of 0. And we just have to know that cosine of 0 is 1 and sine of 0 is 0 to get it. So that's a proof. Property 2 says that complex exponentials satisfy the law of exponents. Times alpha plus beta equals e to the j alpha times e to the j beta. Adding exponents is multiplying numbers. 3. The usual differential rules hold. D by d theta, e to the j theta, equals j e to the j theta. And property 4, I'll simply say it this way. Power series are consistent. By consistent, I mean that if I plug in the power series for E on the left-hand side of Euler's formula and the power series for cosine and sine in on the right-hand side, I get an equality. When I prove 4, I'll remind you about these power series. And remember, the main thing to carry away from this video is that Euler's formula gives a consistent definition of complex exponential. Let me give a short word on the logic of what we're doing here. Before Euler's formula, we have no definition of what it means to raise e to a complex power, so we can define it any way we like. Then it's incumbent on us to show that this is a good definition, that it's consistent with all the usual properties of exponentials. That's what we're doing in this video. You may have seen Euler's formula as a consequence of one of these other properties. That will work too. You can start with properties 3 or 4 as the definition and then derive Euler's formula and properties 1 and 2 from that. Here we choose to start with Euler's as the definition. Let's prove these properties now. We proved the first one, that e to the j0 was 1. Let's prove property 2, that the law of exponents holds. To do that, here's property 2. We have to look at e to the j alpha times e to the j beta. Well, we use Euler's formula for the definition of complex exponentials, and this is cosine alpha plus j sine alpha times cosine of beta plus j sine beta. Now we expand that out and do our usual thing. The real part is cosine alpha cosine beta minus sine alpha sine beta. If you see, there's a j squared times that, but j squared is minus 1, plus j times cosine alpha sine beta plus sine alpha cosine beta. I'm going to squeeze that in here. You know what it equals. Now, we have to look at each term and recognize the trig identity. This term right here is the cosine addition formula. So that expression becomes cosine of alpha plus beta, and then plus j, and you have to recognize this as the sine addition formula. That's sine of alpha plus beta. And now once again, by definition, Euler's formula says that this cosine alpha plus beta plus j sine alpha plus beta is none other than e to the j alpha plus beta. So there we've shown it. The law of exponents holds. We have room now to fit in property 3 on this slide. Property 3 says complex exponentials differentiate correctly. So we have to look at d by d theta. Here's the left-hand side of that identity, e to the j theta. That equals d by d theta of cos theta plus j sine theta. And this is an easy derivative. Derivative of cosine theta is minus sine theta plus j. Derivative of sine theta is cosine theta. Now let's show that this derivative equals the right-hand side of identity 3. The right-hand side is j times e to the j theta. We should show that these two things are the same. Well, we just use Euler's formula and expand this out. Cosine theta plus j sine theta. When I multiply by j, I get j cosine theta. And of course, j squared sine theta is just minus sine theta. And now it's easy to see that these two things are the same. And therefore, these two things on the left are the same. That's identity 3. I get to write QED. Now let's tackle property 4, the consistency of power series. Rather than watch me write out all the power series, I've prepared them ahead of time. So I'll remind you, e to the x is a power series 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. That's what the dot 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 means. Cosine theta is 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial, etc. Has the even powers of theta alternating in sign. Sine of theta is theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, etc. This has the odd powers of theta alternating in sign. I'm assuming somewhere in your past you've seen these. As I said, the main lesson to carry away from this is that Euler's formula is consistent with power series. Before substituting these power series into Euler's formula, let's just look at powers of j. This is simple. Of course, j to the 1 is just j. J squared equals minus 1. J cubed equals minus j. J to the 4th equals 1. Now let's do the proof. We'll plug the power series for each of these things into the appropriate parts of Euler's formula. On the left-hand side, we have e to the j theta, and so that equals 1 plus j theta plus j theta squared over 2 factorial plus j theta cubed over 3 factorial. I think a 4th power will be enough. J theta to the 4th over 4 factorial. Use the dot 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 for all the missing terms. Let's try to squeeze that in on the right here. That equals 1 plus j theta. J squared is minus 1, so theta squared